Hey, welcome. Today we're going to be talking about conservation of angular momentum. So we are continuing our discussion in our unit in momentum for AP Physics C Mechanics. And what I want to talk about is this figure skater right here and what she's actually doing, and also relate it to concepts that we've already thought about in rotation and in momentum. So it turns out for our purposes, momentum is largely conserved. That means you have the same amount of momentum before an event as you have after an event. And the same goes for this. My question, first of all, to you would be, what's the event as this figure skater is skating? What do you think? Well, hopefully you can tell that the event is she brings her arms and her leg closer to the center of the axis of rotation. So she's actually changing something. What is it that she's changing that we've talked about in the context of rotation? She's changing her moment of inertia, or her rotational inertia, her I value, because the closer the mass is towards the center of the axis of rotation, the lower the I value is in general for objects. So she can do that. She can change her moment of inertia, which actually changes the rate at which she spins, her angular speed or angular velocity, her omega value, which is pretty amazing. So if you understand the physics, you can understand why she's getting faster and faster. So let's go ahead and take a look at some of these concepts here. First of all, I do want to say that yes, momentum is conserved for pretty much everything that we do for the most part. There's one technicality that someone could object with and say, well, there is a case where if there's a net external force on the entire system, then you could say that momentum is not conserved. That is true, but then you could counter with, well, if you just increase the size of the system, then that would encompass that net external force, and then momentum would still be conserved. So for our purposes, generally speaking, when in doubt, just consider momentum to be conserved. And if you are dealing with a problem where there's a loss of energy due to friction, for instance, then you need to consider momentum, right? Whereas kinetic energy is not always conserved. You could have an inelastic collision, for instance, and some of that kinetic energy goes into heat or friction or something along those lines. So we could say, when in doubt, go with momentum, but if you can use energy, then you are probably expected to use energy for solving problems. Now, angular momentum is an extension of that. It's just like momentum in a rotational sense. So that's what we're going to be talking about today. So let's go ahead and take a look at what you would see on your equation sheet. So this is your equation on your equation sheet. This L value stands for angular momentum. It is a vector. And this R value is the distance between the axis of rotation and crossed with the momentum, the linear momentum at that distance. I'm going to show you a GIF animation at the end of this screencast where you'll see what I'm talking about for these two vectors. Primarily, we're going to be dealing with these values over here and this over here. So the two outside parts of this three-part equation, you could say, for today. All right, so the first statement we could make is that her initial angular momentum is equal to her final angular momentum. And so we could say I initial omega initial is equal to I final omega final. So we could say, well, what actually happened? So remember, she has, what do you think, a larger or a smaller I value initially? So at the very beginning, right about now, her I value is going to be larger than at the final location because she brings her arms and her leg toward the center of the axis of rotation. So as a result, what we could do is say this I value is greater, this I value is lesser. And what does that necessarily and mathematically do to the omega initial and the omega final? Well, that would mean the omega initial would be lesser and the omega final would be greater. I'm going to simplify this by just showing you some very simple numbers so you get the idea. If this first number is much greater and this first number is lesser and they are equal to each other, then the inverse must happen with the second numbers that are multiplied with the first. In other words, they're inversely proportional to each other. Alright, so let's go ahead and apply the same concept, the exact same concept with some numbers and see how it all works out. So let's say there's a student on a roundabout, standing on the perimeter of the roundabout, and he's going to walk towards the center, and he'll not quite get to the center over here, but he's going to change his position. And I want you to think about, just like the figure skater in the first example, what do you think we're going to end up with? Alright, well that omega initial is going to increase when it gets to the omega final position, just like our I initial is going to decrease. So let's go ahead and see how to do this problem. So first of all, we can go ahead and look at the equation that's on our equation sheet again. We're going to use the two outside parts of this three-part equation and state that the initial angular momentum is going to be equal to the final angular momentum. And we're going to go ahead and solve for omega final. And we just have to do a couple calculations for rotational inertia initial and rotational inertia final. So we're going to go ahead and solve for that. What's our initial? Well, we have to sum up the initial rotational inertia of the students and the initial rotational inertia of the roundabout. And what's going to happen is, notice here her R value is 2 meters because she starts on the edge of the roundabout, and so we have to take that into account. We do the math here and we end up with 490 kilograms times meters squared. Now try to remember that number because that number is going to be greater than what we're going to calculate for the final rotational inertia. So let's go ahead and take a look at that. If we calculate the final rotational inertia, this is the rotational inertia of the student final. So we go ahead and do the same calculation, except her radius value is now different. So we go ahead and plug in the different radius value here, and we end up with a lesser number for our rotational inertia final. And so what that means is exactly what you might expect. At least I hope you would expect. So what do you think? Is this thing going to speed up or slow down? Well, it's going to speed up just like the figure skater sped up. So if we do the math, it turns out that it's 4 radians a second. And so it does get faster just like we would expect, but that's using numbers and units that you should become familiar with. Alright, and the last thing I want to point out is there is a GIF animation here that I think is actually incredibly helpful if you understand what the GIF animation is showing. It's showing the vectors that are involved for torque and for angular momentum. And I've done a whole lesson just on interpreting this three-dimensional thing called a right-hand rule. And so this is a mnemonic device that will help you to determine the direction of the vectors that are involved for this sort of complex scenario. I just wanted to introduce this GIF animation though because I think if you pay attention to the dark green arrow right there and the red arrow, I think it can help you to understand what we're talking about when we cross a R vector with a P vector and what exactly that does. So in any case, I hope this has been helpful. If you have any comments down below, please let me know, and I hope you all have a great day. Take care.